Hello, this is Math 2115 coming to you from the College of DuPage for fall of 2020, and the title of this lecture is Logic. Let's begin with a definition of what proposition is. A sentence that is either true or false, but not both, is called a proposition. And so if we look at these things, we see that A through D are propositions. Now, it turns out either Earth is the only planet in the universe that contains life, or it's not, once you figure out what life is. And these other things, I think, are true. Actually, I don't know about the Alfred Hitchcock thing. But E and F aren't, because F depends on what X is, whether it is true or false. And it could be true if X is 2, but it could be false if X is not 2. And buy 2 tickets to the Unhinged Universe rock concert on Friday is an order, but it's not true or false. So we will be dealing with propositions, and we're going to be talking about letting variables called P, Q, and R represent propositions, which are sentences that are true or false, but not both. And we do operations on these. So let P and Q be propositions. Then we say the conjunction of P and Q, denoted P, this is an inverted V, and Q, is the proposition P and Q. The disjunction of P and Q, denoted P, this is a right side up V, Q, is the proposition P or Q. Now, we build truth tables for these things. So a truth table for a proposition is we want to list all the possibilities for the constituent propositions. So this is a combined proposition involving these 3 subcomponents. So here you've got 3. So this one could be true or false. This one could be true or false. And this one could be true or false, independently one with another. So we get 8 possibilities. The easiest way to list the 8 possibilities is to go 4 T's, 4 false, 2 T's, 2 false, 2 T's, 2 false, and alternate TFs. And that gets all the values there. So that's all the possible combinations. So those are what you have to evaluate. So let's look at then the truth table for P and Q. And this is the definition, but P and Q is true only when both P and Q are true. Otherwise, it is false. This is the disjunction, but it's also sometimes called the inclusive or, because it allows both of them to be true, and this is the definition for it. There can be different ones called exclusive or, and there's some exercises there that we deal with that, but this is what we mean by the disjunction or inclusive or of P and Q, and it's defined with this truth table. And the only time this is false is when both P and Q are false. Another operation we have is called the negation of P, and this is this angled down, it looks like an Allen wrench kind of, but it's an angled down symbol in our book. P is the proposition not P, and the way we define that is if P is true, not P is false, and if P is false, not P is true. We do have an order of operations. So in the expressions involving some or all of the operators, negation, conjunction, and disjunction, and in the absence of parentheses, because we still always do parentheses first, the innermost parentheses first, we first evaluate the negative, then we do and then we do or. Such a convention is called an operator precedence. In algebra, operator precedence tells us to evaluate multiplication and division from left to right as we run across them before plus and minus. And the left to right as you run across them also applies in the logic calculations. Okay, so here is an example of kind of problems, and I would like for you to do a couple of these. So right now, I want you to write a truth table for each proposition, and actually we're not going to do 23 through 30, we're going to do 28 and 30. I'm doing this because I expect you to pause the video, try these, and then return, and we'll see how you do. It's almost like a recitation. So you know what to do. Now we're going to see how you did. So for 28, you should have gotten a final truth column of FF, TT, TTTT for this value, this set of values. And you notice this is filled out the way I suggested you should. Similarly, this is filled out the same way. Here you should have gotten TF, TTT all the way down. And in fact, what you see from this is that these two are not the same because it's different up here. Let's continue then. If P and Q are propositions, the proposition if P then Q is called a conditional proposition and is denoted by P with an arrow going to the Q. The proposition P is called the hypothesis, or sometimes called the antecedent, and the proposition Q is called the conclusion or consequent. And this is the definition of the truth value of the proposition if P then Q. And the only time it's false is if you have a true implying a false. I sometimes use the example, I guess I'm going to use it with you now. I have a daughter, Beth, and I might tell Beth that we'll do an outing if it doesn't rain. So let P be if it rains, and then Q will be we will do an outing. So if it doesn't rain and we do an outing, I was telling the truth. If it doesn't rain and we don't do an outing, I was lying. If it doesn't rain, we can do an outing or not do an outing, it's still true. These last two bother some people because if the if part is false, it is always true. So a conditional proposition that is true because the hypothesis is false is said to be true by default, or sometimes we say vacuously true. Other words are sometimes used with this. A necessary condition is just that, a condition that is necessary for a particular outcome to be achieved. It does not guarantee the outcome. So for example, if we had if P then Q, we would say that Q is necessary for P. Similarly, a sufficient condition is a condition that suffices to guarantee a particular conclusion. So if we say P, if P then Q, P is sufficient for Q. We call the proposition Q implies P the converse of the proposition P implies Q. Thus, a conditional proposition can be true while its converse can be false. You can build a truth table for this and check that these actually can have different truth values depending on which row in the truth table you're looking at. Sometimes I think about this with an example as well. If I have an important meeting, then I will wear a sports jacket. If I'm wearing a sports jacket, does that mean I'm having an important meeting? Not necessarily. Maybe it was the only thing that was clean. Another useful proposition is P if and only if Q, which is considered to be true precisely when both P and Q have the same truth values, i.e. P and Q are either both true or they are both false simultaneously. And so that's the definition we have here. If P and Q are propositions, the proposition P if and only if Q is called a biconditional proposition and is denoted by P if and only if Q, that symbol. Now, it's traditional in mathematical definitions, but only in definitions, not in theorems, to use if to mean if and only if. So you see, we say something is a definition if something is true, and if something is true, then it's one of those things as well. An example of this would be a right triangle. If we have a triangle with a 90-degree angle, we call it a right triangle. It's really if and only if, but this is only true with definitions. In some cases, Two propositions have the same truth values no matter what truth values their constituent propositions have. These are called logically equivalent, and this is the symbol we use. We're not just saying they're equal, but we're saying with three strokes that they're logically equivalent, meaning they always have the same truth value. One of these laws is called De Morgan's law, and you see if we take the negation of P or Q, that is considered to be logically equivalent to negation P, negation Q, but we change the sign in the middle to a conjunction. This is De Morgan's law. This is also called another version of De Morgan's law. Negation P and Q is negation P or Q. I'm going to ask you to prove this first one here. So please do that. Let's see how you did. So you should have said, well, I just have P and Q, so I list the possible truth values. Notice here I do TTFF, TFTF, and for this one I get this, and for this one I get this. But notice that these truth columns are the same. That means that they're logically equivalent. Here's a problem for you to give a go. Show that the negation of if P then Q is logically equivalent to P and not Q. And notice that we now, if we do the negation of this, we can write it without any implication. You know what to do. Let's see how you did. And you should have gotten this. You see that the truth columns are the same. That means that they are logically equivalent. Here's another one for you. So take this one and show us logically equivalent to this one. You know what to do. Let's see how you did. So if you work through this, what you find that this one is going to be TFFT, and this one is also going to be TFFT. I will be asking you to do truth tables, so make sure you can do these kind of things. We conclude this section by talking about the contrapositive of a conditional statement. And so the contrapositive, or sometimes called transposition, of a conditional proposition P implies Q, if P then Q, is the proposition not P implies not Q. So you could say, if I am wearing a suit jacket, or excuse me, I'll say it a different way. If I have an important meeting, then I will wear a suit jacket. If I'm not wearing a suit jacket, then I don't have an important meaning. You should notice the difference between the contrapositive and the converse. The converse of a conditional proposition merely reverses the roles of P and Q, whereas the contrapositive reverses the roles and negates each of them. And here's a theorem, and you prove this by making a truth table. The conditional proposition, if P, then Q, and its contrapositive, if not Q, then not P, are logically equivalent. Well, we build truth tables, and we find that both of them have the same truth tables. Therefore, those are logically equivalent. This is kind of a powerful statement. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.